Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. In the grand theatre of the cosmos, as perceived by the flourishing Gupta Empire in 5th century India, celestial events were episodes of profound mythological drama. An eclipse was a moment of cosmic terror and divine intervention. The story, woven into the very fabric of the Puranas and cultural consciousness, spoke of the Asura, or demon, Rahu. Through cunning, Rahu had managed to sip the nectar of immortality, the Amrita. Before the divine elixir could pass his throat, the sun and moon, Surya and Chandra, alerted the god Vishnu, who swiftly decapitated the demon. The immortal head, Rahu, and the writhing body, Ketu, were condemned to wander the heavens forever. In an act of eternal vengeance, Rahu periodically pursues and swallows the sun or moon, plunging the world into a temporary ominous darkness. The eclipse ends only when the celestial body slips through his severed neck. This was the explanation, a narrative of immense power, satisfying the human need for meaning, for cause, and for a universe animated by intention and will. It was a cosmos understood through story. Into this world of divine narrative, a world where the motions of the planets were the paths of gods and the shadows in the sky were the actions of vengeful demons, stepped a solitary and revolutionary intellect. From the heart of the Gupta Golden Age, a period of extraordinary cultural and scientific flowering, emerged a voice that proposed a different kind of cosmos. This universe was animated by a different force, the serene, implacable, and predictable logic of number. This was the world of Aryabhata. His great intellectual challenge, and indeed his legacy, was the monumental task of supplanting a universe of myth with a universe of mathematics. He sought to demonstrate that the swallowing of the sun by a demon was a less compelling explanation than the precise, predictable transit of the moon's shadow across the face of the earth. To do so required a new language, a new authority, and a new way of thinking. His authority would derive from calculation, his language would be geometry and algebra, and his proof would be the power of prediction. Born, it is believed, in the year 476 of the Common Era, Aryabhata composed his masterwork, the Aryabhatiya, at the age of 23 in the city of Kusumapura, often identified with the imperial capital, Pataliputra. The text itself is a marvel of compression, a distillation of an entire system of mathematics and astronomy into 121 concise stanzas of Sanskrit verse. This poetic form was a common mnemonic device in ancient Indian scholarship, enabling complex rules and vast tables of data to be committed to memory and transmitted across generations. The Aryabhatiya is a work of immense density, a treatise where every syllable carries weight. It presents a complete system, a computational engine for understanding the heavens. Its purpose was profoundly practical, to provide the tools for accurate calendrical calculations, for determining the positions of the planets, and for predicting the timing and circumstances of those very eclipses that so terrified the popular imagination. The architecture of this intellectual edifice is as elegant as it is logical. Aryabhata organized his knowledge into 4 distinct sections, or padas, that build upon one another with a beautiful inevitability. This structure provides a map, a guide to his thought, and it will serve as the framework for our own journey into his world. The first section is the Gitikapada, or the section of 10 Giti stanzas. This is the overture, a highly condensed summary of the fundamental astronomical parameters of his system, presented in a unique alphabetical coding scheme. Here we find the vast cycles of time, the number of rotations of the planets in a cosmic age, or Mahayuga, and the circumference of the great celestial circles. It is the foundational data, the essential constants upon which the entire cosmic model rests. From these celestial fundamentals, the text proceeds to the terrestrial tools of calculation in the second section, the Genitapada, or the section on mathematics. This chapter lays out the essential mathematical algorithms required for the astronomical work to follow. It is a concise handbook of 5th century Indian mathematics, covering arithmetic operations, geometry, plane and spherical trigonometry, and most remarkably, sophisticated methods for solving algebraic equations. Here Aryabhata provides the intellectual toolkit, the pure mathematics that empowers the astronomer to move from abstract parameters to concrete predictions. Our own analysis will soon turn to the remarkable contents of this section, for it contains some of his most enduring contributions to the history of mathematics. The third section, the Kalakriyabada, or the section on the reckoning of times, applies the mathematical methods of the Genitapada to the astronomical constants of the Gitikapada. Here, the system comes alive. Aryabhata details the methods for determining the mean and true positions of the planets for any given day. He establishes the divisions of time, from the smallest units to the great aeons, and defines the structure of the week and the civil calendar. This section transforms the static cosmic blueprint into a dynamic working model, a clockwork universe whose gears and levers are the rules of arithmetic and trigonometry. It is a manual for the practical astronomer, the court astrologer, and the calendar maker, demonstrating how to harness the power of number to master time itself. The final section, the Galapada, or the section on the spheres, represents the theoretical culmination of the entire work. Here, Aryabhata presents his vision of the cosmos as a series of concentric spheres. He discusses the celestial equator, the ecliptic, the motion of the equinoxes, and the fundamental principles of spherical astronomy. It is in this chapter that we find his most audacious and celebrated claims, a heliocentric component to his model, and the assertion that the Earth itself spins on its axis to produce the daily rotation of the stars. He provides the geometric and physical reasoning for celestial phenomena, including a brilliantly simple and accurate explanation for solar and lunar eclipses, attributing them to the casting of shadows by the Earth and the Moon. The demon Rahu is banished, replaced by the elegant interplay of light and geometry. The Aryabhatiya, therefore, presents a complete, self-contained system for understanding the cosmos through reason and calculation. It is a declaration of independence from mythological explanation. Its 4 sections represent a logical progression from foundational data through mathematical tools to the application of those tools in timekeeping, and finally, to a full-fledged geometric model of the universe. To follow the path Aryabhatiya laid out is to witness the construction of a new reality, one built of numbers, angles, and ratios. Our exploration of his profound achievements will proceed along this very path, beginning, as he did, with the foundational mathematics that made his revolution possible. We will delve into the Genitapada, examining the specific problems of calculation he faced, and the ingenious algorithms he devised, which would echo through the corridors of science for more than a millennium. Within the 33 dense verses of the Genitapada, or On Mathematics, Aryabhatiya establishes the computational bedrock for his entire cosmic system. This section is a masterclass in algorithmic thinking, a sparse and powerful collection of rules designed for efficient, repeatable calculation. The intellectual landscape of 5th century India demanded such tools. Astronomy required the prediction of planetary positions over vast timescales. a task involving immense numbers and the resolution of complex cyclical relationships. Commerce and civil engineering likewise presented problems of measurement, allocation, and geometry that required systematic, reliable methods. The Ganatapada is Aryabhati's definitive answer to these challenges, a set of mathematical instruments forged with extraordinary precision and foresight. Foremost among these instruments is his celebrated method for solving linear indeterminate equations, a class of problems that seeks integer solutions for variables locked in a linear relationship. An equation of the form ax plus by equals c, where a, b, and c are known integers, might seem abstract, yet it lies at the heart of many astronomical puzzles. Consider the task of determining when two planets with different orbital periods will return to a specific alignment. This requires finding whole numbers of orbits that satisfy the celestial geometry, a classic indeterminate problem. Aryabhati's procedure for this, which he called Kutaka, a name meaning the pulverizer, is a testament to his algebraic genius. The method operates through a process of successive reduction, a recursive algorithm that pulverizes the large coefficients of the equation. By repeatedly finding remainders in a manner that mirrors the Euclidean algorithm for finding the greatest common divisor, the problem is broken down into a simpler form from which a solution can be constructed. Working backwards from this simplified state, the algorithm reassembles the components to yield the integer solutions for the original equation. This elegant iterative process represents the earliest known systematic method for solving such equations and is, in its essence, the direct intellectual ancestor of the extended Euclidean algorithm, a cornerstone of modern number theory and cryptography. His algebraic prowess extended into the realm of series and progressions. The ability to sum a sequence of numbers following a regular pattern was vital for calculating cumulative effects, such as the total area of a complex shape composed of stacked rectangles, or the total distance traveled by an object under uniform acceleration. Aryabhata provides concise rules for the summation of arithmetic progressions, a foundational skill for any quantitative science. He ventures into far more sophisticated territory by presenting formulas for the sum of the first n squares, and quite remarkably, for the sum of the first n cubes. His rule for the latter is a moment of pure mathematical elegance. The sum of the cubes of the first n integers is equal to the square of the sum of those same integers. This profound identity reveals a deep structural understanding of number theory, demonstrating a capacity for abstract generalization that moves well beyond immediate practical necessity. These formulas equipped astronomers and engineers with powerful shortcuts for complex calculations that would otherwise demand laborious, element-by-element summation. The practical demands of geometry, particularly in construction and land surveying, necessitated accurate methods for extracting the roots of numbers. Aryabhata addressed this with clear step-by-step algorithms for determining both square and cube roots. His method is strikingly similar to the long division style of root extraction that would be taught in schools across the world more than a millennium later. It is a digit-by-digit process, one that requires a sophisticated grasp of the place-value principle and the underlying structure of binomial expansions. To find the cube root of a large number, for example, his algorithm effectively partitions the number into groups of digits and systematically subtracts the largest possible cube at each stage, a procedure that implicitly relies on the expansion of the quantity a plus b, all cubed. This provided a reliable, universally applicable technique for finding lengths from known areas or volumes, a critical skill for the precise execution of architectural and astronomical designs. Perhaps the most famous and consequential calculation in the entire Ganatapada concerns the ratio of a circle's circumference to its diameter. The quest for the value of pi's is an ancient one, and previous Indian texts offered approximations like the square root of 10, a value around 3.16. Aryabhata pursued a far higher degree of precision. In a celebrated verse, he gives the following instruction: add 4 to 100, multiply by 8, and then add 62,000. The result is approximately the circumference of a circle whose diameter is 20,000. This calculation, 100 plus 4 multiplied by 8 plus 62,000, yields a circumference of 62,832 for a diameter of 20,000. The resulting ratio, 62832, divided by 20000, simplifies to 3.1416. This 4-decimal place approximation was the most accurate value for pi available anywhere in the world at the time, and would remain so for over 1,000 years. The numerical result itself is a monumental achievement. Yet, the true depth of Aryabhata's insight is revealed in a single, carefully chosen word within the verse, asana. This Sanskrit term translates as approaching, nearing, or approximate. By explicitly qualifying his extraordinarily accurate value as an approximation, Aryabhata signals a profound conceptual leap. He is communicating that his value is a close estimate, a boundary that one approaches. This hints at a deep intuition, a recognition that the true ratio might be fundamentally elusive, that its exact value is perhaps unreachable through finite division. This stands in stark contrast to the prevailing search for a perfect, rational expression for the ratio. Aryabhata's use of asana suggests an early sophisticated understanding of the nature of an irrational number, an acceptance of approximation as the highest form of truth available for this particular constant. The mathematical tools of the Ganatapada, from the pulverizing power of the Kutaka to the subtle wisdom embedded in his value of p, formed the engine of his astronomical revolution. They provided the means to translate abstract geometric models into concrete numerical predictions. Yet for these algorithms to operate on the colossal numbers required for cosmic timekeeping, an equally powerful system of representing those numbers was essential. The very structure of his calculations implies a deep fluency with a place-value system, raising the critical question of how he encoded these quantities in his terse poetic verses. It is to this innovation, his unique alphabetical system of numeration, that we now turn. The mathematical tools of the Ganatapada, from the pulverizing power of the Kutaka to the subtle wisdom embedded in his value of p, formed the engine of his astronomical revolution. They provided the means to translate abstract geometric models into concrete numerical predictions. Yet for these algorithms to operate on the colossal numbers required for cosmic timekeeping, an equally powerful system of representing those numbers was essential. The very structure of his calculations implies a deep fluency with a place-value system, raising the critical question of how he encoded these quantities in his terse, poetic verses. It is to this innovation, his unique alphabetical system of numeration, that we now turn. The challenge facing any astronomer of antiquity was one of scale. The heavens move in cycles of immense duration, demanding numbers that strain the expressive capacity of common language and conventional notation. Earlier systems, often relying on additive principles where symbols are repeated and summed, become profoundly cumbersome when dealing with figures in the millions or billions. A calculation involving the 4,320,000 years of a Mahayuga would require a sprawling, error-prone representation. The intellectual environment called for a method of supreme economy, a way to capture and manipulate these vast quantities with both precision and brevity. Such a system would need to be more than a simple catalogue of symbols. it would need an internal generative logic. Aryabhata's response to this challenge is a marvel of intellectual engineering, a system of numeration so compact that it allowed him to embed the fundamental constants of his cosmos directly into the metrical fabric of his poetry. He devised an alphabetical cipher, a method that assigned numerical values to the consonants of the Sanskrit alphabet. This system is one of breathtaking density, a form of data compression that would be the envy of a modern software engineer, albeit one with a deep appreciation for Sanskrit prosody. The mechanics of this system reveal a profound understanding of the place value principle. Aryabhata divided the consonants into two groups. The 25 varga, or classified consonants from ka to ma, were assigned the values 1 through 25. The 8 varga, or unclassified consonants from ya to ha, took the values 30, 40, 50 and so on, up to 100. These consonants formed the raw digits of his system. The true ingenuity lies in how these values were compounded and magnified. Aryabhata linked this consonantal system to the vowels of the alphabet. Each of the 9 vowels from A to L corresponded to a successive power of 100. A consonant followed by the vowel A represented its base value, effectively multiplied by 100 to the power of 0. A consonant followed by the vowel I was multiplied by 100. One followed by U was multiplied by 10,000, which is 100 squared. This exponential progression continued through the vowels, allowing for the construction of astronomically large numbers from a handful of syllables. To form a number, one would combine consonants and vowels into a single, pronounceable, and metrically viable word. For instance, in the opening verses of the Gita-Pada, Aryabhata famously encodes the number of solar revolutions in a Mahayuga, 4,320,000, in the single word hu-spit. Let us deconstruct this remarkable piece of numerical poetry. The word is composed of 2 primary phonetic units, hu-spit. In the first unit, hus, the consonants are qs, representing 2, and y, representing 30. Added together, they yield 32. This value is then modified by the vowel u. As the third vowel in the sequence, u signifies a multiplication by 100 squared, or 10,000. Thus, q's q spit, q spit, q spit, q spit. The second unit is git. Eu spit. The consonant q spit represents 4. It is modified by the vowel u spit, the fourth in the sequence, which signifies a multiplication by 100 cubed, or 1 million. This gives a value of 4 million. Combining the two parts, 4 million plus 320,000, yields precisely 4,320,000. A cosmic constant, captured in a single 4-syllable word. This system, while appearing additive at the syllabic level, is fundamentally rooted in a place value conception. Each vowel effectively defines a place: the place of 100, the place of 10,000, the place of 1 million, and the consonant or consonant cluster provides the digit for that place. This is a base 100 system of extraordinary power. It equipped Aryabhata with the capacity to write down any number he required, however large, and to do so within the strict confines of the Arya meter he employed for his treatise. This ensured the accurate transmission of his work, as the numbers were an inseparable part of the verses themselves. A scribe, making an error in a number, would also break the poetic meter, a self-correcting mechanism of profound elegance. This brings us to one of the most debated and significant aspects of Aryabhata's numerical thought, the concept of zero. Within the alphabetical cipher of the Aryabhatiya, there exists no distinct symbol for zero. Yet, the entire logical structure of his place value system depends on it. When he writes Q's Peats for 4,320,000, he is explicitly stating a value for the 10,000s place and the millions place. The absence of syllables corresponding to the units, tens, hundreds, or thousands places, is itself a piece of information. It is a structured void, an absence that gives meaning and position to the values that are present. The system's architecture reveals a profound grasp of zero's placeholder function, a structural necessity for the scheme to operate. The concept of shunya, or emptiness, was a familiar one in Indian philosophical traditions, and here we see its mathematical counterpart emerging. It is a conceptual zero, a placeholder understood and required by the rules of the system, preceding the invention of a specific glyph like the dot or circle that would later come to represent it. This intellectual step is of monumental importance. It represents a cognitive revolution, a new framework for conceptualizing quantity itself. The ability to signify a positional vacancy is the bedrock of all modern arithmetic. The enduring legacy of this alphabetical numeration lies in its demonstration of a fully operational place-value system. While this specific cipher was perhaps too complex for everyday commerce and was eventually superseded by the simpler Brahmi-derived numerals, its intellectual contribution was immense. It established and normalized the principle of positional value in the highest echelons of Indian science. This very principle, combined with 10 base digits including a symbol for zero, would evolve into the Hindu Arabic numeral system, the universal language of modern science, technology, and finance. Aryabhata's poetic code was a critical ancestor, a proof of concept that demonstrated how the power of number could be unleashed through the logic of position. It was the language he invented to speak of the cosmos. With this powerful numerical language established, capable of expressing the grandest scales of time and space, Aryabhata could now construct the geometric machinery to populate it with data. He required a precise method for linking the angles of celestial observation to the linear distances within his models, a tool that would become the very foundation of modern trigonometry. The intellectual apparatus for expressing vast cosmic quantities was now in place. Aryabhata's alphabetic cipher, a dense and poetic system, had established the necessary framework for handling large numbers with positional elegance. Yet, a language of quantity alone is insufficient for cosmology. To map the heavens, one requires a geometry of motion, a precise mathematical bridge connecting the angular sweep of a planet across the sky to the linear distances within a cosmic model. The astronomical tradition inherited from the Hellenistic world, particularly through Claudius Ptolemy's monumental Almagest, possessed such a tool, the table of chords. A chord is the straight-line segment connecting 2 points on the circumference of a circle. While effective, this tool carried with it a certain geometric indirectness. Calculating the properties of triangles inscribed within a circle using chords often involved multiple steps and cumbersome relationships. The challenge for the astronomers of Gupta-era India was the refinement of this geometric machinery, seeking a more direct, more computationally fluid method for their increasingly sophisticated models of the cosmos. Aryabhata's response to this challenge, presented in the Gita-Kapada section of his work, represents one of the most pivotal conceptual advancements in the history of mathematics. His approach centered on a different fundamental quantity, the Ardha Jaya, which translates from Sanskrit as half-chord. The full chord, or Jaya, spanned an arc, but Aryabhata perceived that the essential geometric relationship for astronomy lay within the right-angled triangle formed by the radius, a perpendicular from the radius to the chord's endpoint, and the half-chord itself. This half-chord, the Ardha Jaya, is functionally identical to the modern sine function. It directly relates an angle at the center of a circle to the length of the side opposite it in a right triangle whose hypotenuse is the circle's radius. This was a stroke of profound insight, simplifying the geometry of the circle by focusing on its most fundamental component for astronomical calculation, the right triangle. The entire edifice of trigonometry, the mathematical engine of the physical sciences, finds its direct ancestor in this elegant reframing. The term Jaya, through Arabic translation as Jiba and later Latin misinterpretation as sinus, meaning bay or fold, would ultimately give the world its word sign. Having established this new conceptual foundation, Aryabhata proceeded to construct the necessary practical tool, a table of sign values. This was a task of immense computational labor, requiring both a systematic approach and a high degree of accuracy. He chose a circle with a very specific radius of 3,438 units. This number appears peculiar at first glance, but it is a product of deep mathematical reasoning. A full circle contains 360 degrees, and each degree contains 60 minutes of arc, for a total of 21,600 minutes. The circumference of a circle is given by the formula 2 times pi times the radius. By setting the circumference equal to 21,600, Aryabhata could calculate a corresponding radius using the classical Indian approximation for pi of 3.1416, This calculation yields a radius of approximately 3,437.74. By rounding this to the integer 3,438, he created a system where the sign values, which are lengths, could be expressed as whole numbers with remarkable precision, thereby sidestepping the computational complexities of fractions, a persistent challenge for ancient mathematicians. Within this framework, he divided the first quadrant of the circle, from 0 to 90 degrees, into 24 equal segments. Each segment, therefore, subtends an angle of 3 degrees and 45 minutes. His goal was to tabulate the sign values for the cumulative angle at each of these 24 steps. The result was a list of 24 numbers representing the signs of angles from 3 degrees 45 minutes up to 90 degrees. These values, encoded in his alphabetic numerals, formed the core of his trigonometric system. An astronomer could use this table, through interpolation, to find the sign of any required angle, and thus solve for unknown distances and positions in their geometric models of the heavens. The table itself is a monumental achievement. The true genius, however, lies in the method Aryabhata provided for its construction. He presents the first value in the table, the sign of 3 degrees and 45 minutes, as 225. For the remaining 23 values he provides a single, incredibly concise verse that outlines a recursive algorithm. This algorithm allows for the generation of each successive sign value based on the ones already calculated. The process he describes is, in modern language, a second-order finite difference equation. To understand its elegance, consider the task. After calculating one sign value, one could, in principle, return to the geometric diagram and perform a new independent calculation for the next angle. This would be laborious and prone to accumulating errors. Aryabhata's method was far more sophisticated. He provided a rule for calculating the differences between successive sign values. The first difference between the sign of 0, which is 0, and the sign of the first interval, which is 225, is 225. The second difference between the first and second sign values would be slightly smaller. The third difference would be smaller still. Aryabhata's rule explains precisely how to calculate this decrement. The instruction, unpacked from its poetic form, states that to find the next difference one takes the previous difference and subtracts a specific quantity. This quantity is calculated by taking the sum of all the sign values computed thus far and dividing that sum by the first sign value of 225. Let us trace the first step. The first sign is 225. The first difference is 225. To find the second sign value, we need the second difference. According to the rule, we take the previous difference, 225, and subtract from it the first sign value, 225, divided by itself. This gives 1, so the second difference is 225 minus 1, which is 224. The second sign value is therefore the first sign value, 225, plus this new difference, 224, yielding 449. This is precisely the second value in Aryabhata's table. To find the third sign value, one would repeat the process. The new difference would be the previous one, 224, minus the sum of the first two signs, 225, plus 449, all divided by 225. This recursive self-referential process continues for all 24 values, with each new sign value helping to generate the next. It is a breathtaking example of early algorithmic thinking. It demonstrates a profound understanding of the inner structure of the sign function, recognizing that the rate of change of the function is related to the value of the function itself. This recursive formula is an intellectual achievement of the highest order. It is an ancestor to the numerical methods that underpin modern scientific computing. The idea of approximating a complex curve by understanding its local step-by-step behavior is the foundational concept of differential calculus, which would be formalized by Newton and Leibniz more than a millennium later. Aryabhata, in this single compact verse, had captured the essence of a differential relationship. He had provided a computational engine of remarkable power and efficiency, allowing for the generation of a highly accurate trigonometric table with a minimum of independent calculations. One can almost sense the intellectual satisfaction, a subtle wit in the design, of creating a system that essentially builds itself from a single starting block and a simple, repeatable rule. The creation of the sign function and the development of a sophisticated method for tabulating its values equipped Aryabhata with a quantitative tool of unprecedented power and precision. This was the mathematical key required to unlock the secrets of celestial motion. With this trigonometric machinery, he could translate the observed angles of planets and stars into a coherent geometric structure, calculating their paths, predicting their conjunctions, and investigating the very mechanics of the cosmos. The abstract beauty of the sign table was now ready to be applied to the grand dynamic puzzle of the heavens, allowing him to construct a revolutionary astronomical system that would challenge ancient myths and set Indian science on a new trajectory. With the sign function forged into a precision instrument, the stage was set for its grandest application, the systematic deconstruction and rational reassembly of the cosmos. The astronomical challenges of 5th century India were formidable, a tapestry woven from centuries of observation, intricate calendrical needs, and deeply embedded mythological narratives. The accurate prediction of planetary positions, the reliable regulation of time, and the explanation of dramatic celestial events like eclipses were matters of immense practical and religious importance. Into this complex arena, Aryabhata brought his uniquely mathematical mind, seeking to replace ambiguity with calculation and myth with physical mechanics. His efforts are principally enshrined in the final two sections of the Aryabhata, the Kalakriya-pada, or reckoning of time, and the Gola-pada, or the sphere. Together, they represent a unified astronomical system of breathtaking ambition and elegance. The Kalakriya-pada lays the temporal foundation for his celestial model. Here, Aryabhata undertakes the fundamental task of defining the units of time, from the smallest fractions to the grand cosmic cycles, or yugas. His work was a profound effort to synchronize the heavens with human activity, to create a calendar that was a true reflection of celestial reality. The precision he achieved was extraordinary. He calculated the length of the sidereal day, which is the time it takes for the Earth to complete one full rotation relative to the fixed stars, as 23 hours, 56 minutes, and 4.1 seconds. This value is astonishingly close to the modern figure of 23 hours, 56 minutes, and 4.091 seconds. The microscopic difference speaks to an observational and computational prowess of the highest order. Equally impressive was his calculation of the sidereal year, the time it takes the Earth to complete one orbit around the Sun. His figure was 365.25868 days. While this is a slight overestimation compared to the modern value of 365.25636 days, it was a remarkably accurate approximation for his time, far superior to many other systems in use. These calculations were the bedrock of his astronomy. They provided the stable, reliable temporal grid upon which the complex movements of the Sun, Moon, and planets could be plotted and predicted. By grounding his system in such precise measurements, he was making a clear statement. The universe operates on a predictable, quantifiable schedule, accessible through the power of mathematics. This commitment to a rational, physical cosmos finds its most audacious expression in the Golopada. In this section, Aryabhata presents a model of the celestial sphere and confronts the most fundamental question of observational astronomy. Why do the heavens appear to revolve around us? The traditional answer was simple and intuitive. The celestial sphere, with the stars fixed upon it, rotates daily around a stationary Earth. Aryabhata proposed a far more elegant and parsimonious explanation. He advanced the theory that the Earth itself rotates on its own axis. This was a revolutionary concept. To explain it, he employed a powerful and beautiful analogy, one that remains perfectly clear to this day. He wrote that a person in a boat moving forward sees the stationary objects on the riverbank, such as trees, as moving backward. In the same way, he argued, to the people on the spinning Earth, the stationary stars in the heavens appear to move westward. The genius of this analogy lies in its appeal to direct everyday experience, to explain a profound cosmic principle. It reframes the problem from one of celestial motion to one of relative perspective. This single hypothesis explained the daily rising and setting of the Sun, Moon, and stars with a sublime physical simplicity. It was a conceptual leap of immense courage, positing a dynamic Earth in a universe of fixed stars. Building on this physical foundation, Aryabhata then turned his attention to the dramatic and fear-inducing phenomena of eclipses. The prevailing explanation was mythological, involving the celestial demon Rahu, who was said to periodically devour the Sun or the Moon. Aryabhata dispensed with this narrative entirely. He offered instead a purely geometric and physical explanation. A lunar eclipse, he stated, occurs when the Moon passes into the deep shadow cast by the Earth. A solar eclipse occurs when the Moon, in its orbit, passes between the Sun and the Earth, casting its own smaller shadow upon the terrestrial surface. This explanation is a triumph of three-dimensional spatial reasoning. It presupposes a spherical Earth and a spherical Moon, both illuminated by a distant Sun. The eclipses are a simple, predictable consequence of their orbital dance, and the shadows they inevitably cast. This model allowed for the calculation of the extent and duration of eclipses with remarkable accuracy. He described how to compute the size of the Earth's shadow, or umbra, at the distance of the Moon's orbit, a key parameter for predicting the specifics of any lunar eclipse. The ability to predict the exact timing and appearance of such a terrifying event, using geometry instead of appeasing a mythical demon, was perhaps the most powerful possible validation of his rationalist approach. It transformed an omen of divine wrath into a beautiful, predictable interplay of light and shadow. To account for the more complex wanderings of the planets against the backdrop of the stars, including their puzzling retrograde motion, Aryabhata employed a geometric model based on epicycles. In this system, which has parallels with the Ptolemaic model dominant in the West, each planet moves in a small circle, the epicycle, whose center in turn moves along a larger circle, the deferent centered on the Earth. This geocentric framework was the standard of advanced astronomy across the ancient world, a sophisticated mathematical device for modeling observed planetary behavior. His implementation of this model was meticulously detailed, with specific parameters calculated for each planet to ensure the resulting paths matched the observational data available to him. The entire system, from the length of the day to the looping paths of the planets, was designed as a cohesive, interlocking mathematical machine, capable of generating the past and future positions of all major celestial bodies. The astronomical system of the Aryabhatiya, therefore, represents a monumental intellectual synthesis. It is a cosmos rendered computable. The work established a universe governed by physical causes and mathematical laws, a place where a spinning Earth creates the illusion of a spinning sky, and where celestial shadows produce the awesome spectacle of an eclipse. This comprehensive quantitative model of the heavens, grounded in observation and powered by a sophisticated new mathematics, marked a pivotal moment in the history of science. It laid down a powerful challenge to older mythological worldviews and established a new paradigm for understanding our place in the universe, one based on reason, evidence, and the profound efficacy of numbers. The shock waves from this new vision would ripple through the centuries, provoking debate, inspiring followers, and ultimately shaping the course of astronomy far beyond the borders of India. The intellectual tremors emanating from the Aryabhatiya were felt almost immediately within the subcontinent's vibrant scholarly communities. A work of such ambition and startling originality could hardly have been met with quiet acceptance. Its fate was to become a lodestar for Indian astronomy, a central point of reference around which subsequent discourse would orient itself, whether in agreement or in fierce opposition. The most consequential of its early critics was the formidable astronomer Brahmagupta, who a century later composed his own magnum opus, the Brahmasputa Siddhanta. In it he subjected Aryabhata's system to a rigorous and at times scathing critique. He took particular issue with the doctrine of a spinning Earth, posing a series of logical and physical objections that would echo for centuries. If the Earth truly spun at such a speed, why would birds returning to their nests find them in the same place? Why would tall objects remain upright? These objections, while appearing sound from a pre-Newtonian perspective, reveal the profound conceptual leap Aryabhata had asked of his contemporaries. Yet in a beautiful instance of historical irony, Brahmagupta's detailed refutation served a purpose he perhaps little intended. By engaging so deeply with Aryabhata's ideas, by dedicating significant portions of his own influential text to arguing against them, he ensured their survival and prominence. He cemented the Aryabhatiya as a foundational text whose principles had to be confronted. The debate he initiated kept Aryabhata's theories alive and at the forefront of astronomical thought, guaranteeing that the questions of a rotating Earth and a mathematically defined cosmos would continue to animate scientific inquiry in India for generations. His critique became an inadvertent vessel of preservation, a testament to the enduring power of an idea that commands a response even from its staunchest opponents. The influence of this compact and powerful work was destined to travel far beyond the Indian cultural sphere. As the center of intellectual gravity shifted westward toward the burgeoning Islamic Caliphate, a massive translation movement began in cities like Baghdad. Scholars, sponsored by enlightened rulers, sought out and translated the great works of Greek, Persian and Indian science into Arabic. Sometime during the 8th or 9th century, the mathematical and astronomical knowledge contained within the Aryabhatiya made this momentous journey. While the precise details of its transmission are subject to scholarly debate, its core content, particularly its powerful trigonometric tools and its decimal place value arithmetic, was assimilated into the Arabic scientific tradition. This infusion of Indian mathematics had a transformative effect. The great Persian polymath, Muhammad ibn Musa al-Khwarizmi, working in Baghdad's House of Wisdom, synthesized these Indian methods with Greek geometry and other traditions. His astronomical tables, or Zij, were heavily indebted to the Indian Siddhantic framework, employing the sine function, the Jaya of Aryabhata, Arabized as Jiba, and eventually Latinized into sinus, as a fundamental computational tool. His treatise on arithmetic, which explained the use of the Indian numerals, was so influential that his own name, al-Khwarizmi, gave us the word algorithm, while the book's title, in Latin translation, Algorithmi de Numero Indorum, forever linked this revolutionary system of calculation with its Indian origins. A few centuries later, another towering intellect of the Islamic Golden Age, the scholar al-Biruni, would engage with Aryabhata's work on an even deeper level. A master of Sanskrit, al-Biruni traveled extensively in India and wrote a comprehensive study of its culture, sciences and philosophy, the Kitab al-Hind. In this remarkable text, he discusses Aryabhata with the precision of a fellow scientist, analyzing his theories, comparing them to those of Brahmagupta and the Greeks, and demonstrating a profound understanding of their mathematical underpinnings. He meticulously examined the arguments for a rotating Earth, treating it as a serious scientific hypothesis worthy of rational consideration. Through the works of figures like al-Khwarizmi and al-Biruni, the key innovations championed by Aryabhata, the decimal system, algebraic methods, and a sophisticated sign-based trigonometry, became integral components of the scientific toolkit of the medieval Islamic world. From there, through further translation into Latin in centers of learning in Spain and Italy, these ideas flowed into Europe, providing the essential mathematical grammar for the scientific revolution to come. Reflecting upon this long and winding journey of ideas, from a 5th century text in Kusamapura to the desks of Renaissance astronomers, one perceives the true shape of Aryabhata's legacy. It is a legacy that resides in the specific tools he perfected, the elegant efficiency of the sine table, the computational power of his algorithms, the concise beauty of his astronomical parameters. These were contributions of immense practical and theoretical importance, forming a new foundation for quantitative science. Yet, the full measure of his achievement transcends these individual components. His enduring impact lies in the profound intellectual and philosophical shift he represented. Aryabhata's ultimate contribution was the establishment of a paradigm, a vision of the cosmos as a rational, coherent, and mathematically accessible system. He championed a scientific ethos that placed its faith in the power of numbers and the consistency of physical laws to explain the universe. The world of the Aryabhatiya is one where awesome and seemingly mysterious phenomena yield their secrets to calculation. An eclipse is a predictable passage of one celestial body through the shadow of another. The daily passage of the sun and stars across the sky is the elegant consequence of our own planet's silent, steady rotation. This was a radical departure from a worldview steeped in mythology, where celestial events were the unpredictable actions of deities. He forged a universe governed by cause and effect, where phenomena could be modeled, their future behavior predicted,
and their underlying mechanics understood through the universal language of mathematics. This insistence on a computable cosmos, on a reality that could be captured in the web of equations and numerical tables, was his most revolutionary act. The courage to posit a spinning Earth, the rigor to build a complete mathematical apparatus to support his model, and the intellectual honesty to ground it all in observation. This combination marks a pivotal moment in the history of human thought. It is the birth of a recognizably modern scientific sensibility. The spirit of this ancient astronomer, therefore, echoes in our own time. It resonates in the fundamental conviction that the universe is intelligible. It is present in every line of code that models a galaxy's formation, in every equation that describes a planet's orbit, and in every scientific theory that seeks to replace mystery with understanding. Aryabhata's work stands as a timeless monument to the human capacity to look upon the vast and complex machinery of the heavens and see, with the clear eyes of reason, a system of profound and accessible order. He demonstrated 1500 years ago that the cosmos was a book written in the language of mathematics, and in doing so he handed us the key to begin reading it.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.